for hosting me this week. So I'm going to speak about some works I did in the last year, especially with Jérôme Bott and Edouard Powell, both at the Toulouse School of Economics now, on, let's say, automatic differentiation. Okay, we'll explain in a moment what I mean by automatic differentiation. So just before starting, I think there is something fun about differentiation, that if you think in terms of computer science, okay, so in terms of CS, thanks to automatic differentiation, so when you use PyTorch or stuff like that, this is something which is easy. Okay, easy. Okay, let's. Okay. Now, if you think about integration now, this is something in terms of computer science which is complicated. Okay, if you want something which is exact, so you know that this is something which is exponential in terms of complexity. Okay, so this is, let's say, more than MTL. Okay, so if you want something exact, and if you want something in the numerical world, okay, you have either, let's say, two options. Either you are doing some, let's say, finite different stuff, and this is not dimension free. And otherwise, you can do stuff like, let's say, Monte Carlo in general, which is dimension free, but which have a very slow rate of conversion. Okay, so this is slow. So you have easy versus slow. Okay. In terms of math now, and the talk today will be mostly on this aspect, things are totally reversed. So integration is something which is trivialized by measure theory. So Lebesgue theory tells you that more or less everything in the world is integrable. Okay, so this is recorded. Some mathematician will die doing that, but okay, everything is nice. And here, everything is terrible. Okay. So when you want to differentiate stuff, it's hard to have some condition telling you you can do it. And I will be especially concerned about one thing here, that imagine, so this is an undergrad question, you have a sequence of function, f of n, converging to some f. Some sense. Now you can differentiate this function. And you're asking the question, who is this guy? And the issue is that, except if you have very strong requirements, okay, you cannot even define this guy. Okay. So all this talk will be somehow to, in, let's say, an optimization / machine learning context, how we can do something about that. Okay. So it will not be a machine learning talk, it will not be an optimization talk, but the inspiration behind that, I will come in a moment, came from optimization and machine learning. But somehow, the only thing that we want to do is to give some condition to complete this diagram. Does this part clear enough? Because the whole 40 minutes afterward will be about. That's it. Yeah.
Is the analogous question on the right side is the same as asking whether you can put the expectation in the limit?
Yeah.
This is the same
question, but
for the derivative.
But for this one, it's somehow trivial with Lebesgue dominance theorem, telling you that if somehow you are bounded, everything plays nicely. Okay, in a very rough version of it. Okay. So the context here is that we are interested in optimization. So let's say that I have some function f that I want to minimize over eventually some set. Okay. And in fact, what we want to do is not doing just one set of optimization, but we have some parametric optimization problem, meaning that you have a function which is both a function of your variable x and some parameter theta. Or if you want to have machine learning terms on the parameter and on the hyperparameters. I will stick with variable parameter here. Subject to the fact that you are in some set eventually itself something which is parametric. And so let's say that you have some parameter that you put inside solution solver, okay, of this problem, and it gives you back some solution of this optimization problem. Okay. Now, something that you can also require when you wrote stuff like that is to say, I would like to know what is the sensitivity of the solution to my hyperparameter. Okay, so what happens, say alternatively, what happens is I slightly change my parameter, my hyperparameter inside this problem. Okay, so somehow it's linked to this very generic and old question on computing the sensitivity to the solution map theta. Okay, here theta maps to x bar x of theta. Okay, here we want to compute the derivative. Okay, so that's what we are going to do, but just first, why asking this question? So the first thing is that because it's an interesting math question, and so the perturbation theory of optimization problem is something which is, like I said, quite old, which was really well studied in control theory by people like Bonance. So there is this nice book, like 600 pages of a whole set of conditions such that things like that. The second question, which is probably why I was concerned about this question at the start, is bi-level optimization. So one of my line of work at the moment is to find good bi-level optimization algorithm. And here, somehow, in this parametric problem, the constraint set here is another optimization problem. So in a weird way, somehow, bi-level optimization is nothing more than constraint optimization, where the constraint is an optimization problem. Okay. So the motivation, the original motivation, that I'm absolutely not an expert, is game theory. Okay. And it was rewrite in machine learning. So for instance, for hyperparameter optimization, for meta learning, neural architecture search, and so on. And the last one, which is a bit more, let's say, general, is to say that when you want to look at architecture where the layers are arbitrarily complex. Okay. So for instance, .NET or CVX layers, stuff like that. What you want to do is somehow to say, okay, I have my forward flow on my architecture, and I want to be able to backpropagate through it. Backpropagating through a complex layer is nothing more than giving you this sensitivity map. Okay. So somehow this question of sensitivity is linked to any architecture where you have something more complex than the linear layer, stuff like that. So far, so good? Okay, so now let me remove the discussion. So I have my parametric optimization problem here, where I give my parameter theta and it gives me back one solution of my problem. One thing that I can do is to write, if everything is well behaved, the optimality condition of this problem, and say that at the end, finding a solution to this optimization problem is nothing more than finding a fixed point to this equation. Okay, where big F here is this application, is this mapping. Okay, so you can rewrite an optimization problem as a fixed point search, okay, when you use as a map the optimality condition. If you have a fixed point equation, you have a generic algorithm, which is to tell you that you can start from some point, okay, and repeatedly apply the fixed point mapping to your previous iterate. Okay. And so this will be our, let's say, our main object here on this talk is the fact that we are going to have a function of theta, which are the initialization, okay? And then the next step, always parametric, is nothing more than f, your fixed point mapping, will be our optimality condition here of the previous iterate, tried by theta. Sometimes I will write theta as the indices like that. Okay, so just to say that any parametric optimization problem can be somehow seen as an iterative algorithm. Okay, so here what I want to do is to somehow make sense of if I have an algorithm, so let's say either forward, backward, or even just gradient descent here, and I want to make sense of what does it mean to take the derivative with respect to the parameter, okay, of this algorithm, and especially what happens when the number of iterations grows to infinity. Okay. That's my main question. Making sense of this expression and having some characterization of what happens when the number of iterations goes to infinity. Okay. So as I wrote here, my setting here would be to have a fixed point operator f, and this iterative algorithm, which is just you repeat the same map. Okay. So what the Banach fixed point theorem tells you that if in a uniform way with respect to theta, you know that this map, just the map, not the iteration, just the map is something which is contracted. It's a contraction, so it means it's Lipschitz with a constant strictly less than 1. Then you know that there exists a unique fixed point. So this time it's in a clean way. There is a unique fixed point, and the iterates of this algorithm converge towards it. So this is the first part of Fn goes to some function f. Here, n is theta. Okay, so yeah.
Sorry, I tried to interrupt you. In 2 slides ago, you say you're interested in when maxiter goes to plus infinity. Are you also interested in the regime of maxiter large but not infinite?
So I will mention some at some point in a rough way this case. Yes.
Okay.
We have metric. So
because
here
in practice we have maxiter very large but not infinite.
clearly. So in practice, here what you also have is that you have linear convergence, and I will give some hypothesis, but to keep things simple, I will focus on the asymptotic point of view, but we have also result in a non-asymptotic setting.
Thanks.
Okay, so here you have your iterates, your parametric iterates, okay? And what I told you is that under some Lipschitz condition, I converge towards some fixed point. Okay? On the other side, what you can do is that you can differentiate or automatically differentiate if you see x, the xt as a program, you can get the derivative. So let's be clear, I won't speak about vector Jacobian product or Jacobian vector product, so meaning forward or back propagation, but everything still applies. I put myself in the more general context of having the full Jacobian, but it changed nothing to focus your attention on what happens if you really use it with, let's say, back propagation. Okay, and you have this arrow. Okay. The question is exactly the same undergrad question: is okay, can I differentiate this stuff, and can I take the limit here? Okay, 2 arrows. here the limit in sense of t going to plus infinity, and here taking just the derivative. Okay.
Quick question.
Yeah.
So do we agree that, so on the previous slide, if t is finite, this will be true, so the limit will be equal to the derivative.
Sorry.
If t is finite, yes, so instead of making t going to plus infinity,
Yes, here.
yes, it will be always true, the limit will match the derivative.
Yeah, the limit. There.
Yeah.
Yeah.
So the,
Yeah, so
accepting
at each step it will be true, provided that you have enough regularity here such that this guy is defined. Yes. So a first case which is favorable, which was studied in the 90s, is the following. If you assume that your fixed point mapping is 2, okay, and you take this iterates. So what you can do is to apply the chain rule, okay, explicitly, and it tells you that the next Jacobian is just the previous one, okay, but you precompose by the derivative with respect to the parameter, okay, to the variable, and you also have the contribution of your parameter. Okay. So let's write for the future a equal to the first derivative and b the derivative with respect to theta. Okay, so you have really this linear recurrence. The Jacobian of the next step is a times the previous iterate plus the derivative with respect to theta. And so the nice thing is that if you have a contractive mapping and you are able to bound the spectral behavior of your derivative with respect to x, then you can prove that the limit of the Jacobian, okay, is the Jacobian of the limit, meaning it's the Jacobian of the fixed point. Okay. So the question is, does it make sense? Okay. Here, I tell you that the biggest singular value, okay, of this matrix should be strictly less than 1. So, yeah, this is sufficient, but not necessary. We will come back in a moment on that point. Okay, so under this condition, the good news is that you have this commutative graph diagram. You can either take the derivative here and then taking the limit, okay, or you can take the limit and then differentiate. It's exactly the same thing. Okay, so this is a small diagram that I wrote at the start for real valued function. So far, so good. Okay. So now, what people typically use these days, more like doing implicit differentiation. Okay. Yes, that was an automatic differentiation, but you may know, for instance, if you do optimal transport, stuff like that, what you will do is to use implicit differentiation. What does it mean? It means that if you have this fixed point equation, you can differentiate it, okay, with respect to theta. And the implicit function theorem tells you that if you assume the invertibility of this map, okay, you can explicitly write down, okay, the derivative of your fixed point, okay, and it's just given by the inverse of this map. So identity minus b, okay, minus 1 times a. Okay, so this quantity will also play an important role. Identity minus. Okay. And so, one thing that you can show, okay, which is easy when you are in setting, is that if this this spectral quantity is indeed slightly less than 1, then everything coincides, okay? And it means that the limit of the automatic differentiation is the solution of implicit differentiation. So when you do implicit differentiation, you are doing the good stuff, okay? Okay, so maybe just a comment here. So this assumption here happens, for instance, when if your application is this one. Okay. So let's say that you have x minus eta phi theta of x, and here you take the gradient. Okay. So say automatically you are doing gradient descent. If you choose your step size is phi theta here is a function which is C2, let's say even C11 or C2. Okay. I will come back. Okay. And eta strictly less than 1 over L if your function is L smooth, then everything plays nicely and it's the revenue plan. I will come back to it in a moment. Okay.
Question.
Yeah.
Just to clarify the statement on the bottom, does the first equality imply that the operator question is invertible? So like you're saying, if the limit exists and it's invertible,
Yeah, you're
it's
right.
both.
You should have had this invertibility condition. Sorry.
So the first equality, the exchange in limit implies that that operator is invertible, and you can do so they're equivalent.
Yeah. Okay. Okay. So I'm not. Are you doing optimal transport here? Some of you. Because I'm not. You are doing a bit. I'm not. That's just an example. Okay. So I don't want to. I want to keep my focus on the general setting, but this is a fun example where everything that I just told you does not apply. So I just want to give you some insights about it. So you know that when you are doing optimal transport, the popular way to do it is to do entropic optimal transport. Meaning that you have this linear problem and you just add some entropy inside. So here, the point is that to solve this problem, okay, that you know, may not know, this is not really that important. I think most of you know that optimal transport is kind of an important topic. There is a very simple algorithm to solve this problem. And this algorithm is called Synchron algorithm. And the only thing that you need to do is to rescale iteratively a matrix of the transport plant at each iteration. So if you look at this, okay, this is a entry-wise division here. This is just multiplication and entry-wise division between vector. Okay. The important fact, okay, here is the fact that it is known that PT here converge so linearly to the optimal transport plant, your objective, okay, and that this transport plant as a function of theta is something which is differentiable. And this is at the heart of a lot of paper with mixing deep learning and optimal transport. The issue is that, okay, let's ask the same question. So PT goes to at P, but you want to put that in a neural network, so you want to differentiate through it. The issue is that if you compute the spectral quantity, this spectral quantity, it's equal to 1. So it means that in some direction, stuff will converge, but not in every direction. And you cannot apply this, let's say, generic result of Gilbert. This is fun because, so typically people inclined to do deep learning with optimal transport are like the MATI one. Okay. I think they are all aware of that. Okay, but to our knowledge, there was no proof that it makes sense to do differentiation of optimal transport solver inside the deep architecture. So the good news is that you can do it. Okay, so every time when people are doing empirical stuff that works, there is a theorem on how. And so what you can show is that the automatic differentiation of Synchron algorithm converge indeed at a linear rate, locally, uniformly in theta. And so you can reverse this limit and differentiation operator. Okay. The proof is a bit involved okay, but still doable and manage to share some similar arguments than the generic one. Okay. So let's put aside the SymCon stuff. Okay, so here what I told you is that I needed to control the spectral quantity associated to B. Okay, and sometimes it's you can have it directly. So for instance, for F, for gradient descent, sometimes not. Okay. So another issue, I know that modern architecture doesn't use the value anymore, but let's say, is that you have a lot of optimization problem where you have non-smooth space. Okay. You have non-smooth function, and you are taking automatic differentiation of non-smooth stuff. So here we were initially in this diagram, we discussed a lot about taking the limit here. And I want just to spend a bit of time here. So that was so x, j of x, here x bar, and so here. Well, so I want to discuss a bit what does it mean to take the automatic differentiation of something which is not smooth, taking the derivative of something which has no derivative. Okay. So the first thing is that let's forget about this theoretical concept and try to play a bit with jets. So what you do is you take your value function, okay, and you ask him what is the gradient of volume at 0. So here, I'm asking what is the derivative at this point of this function. The answer is 0. Does it make sense? Yeah, it does. So somehow this thing is a convex function. Okay. You can, for instance, think about subgradients, subdifferential. Yeah, why not? Okay, so now if you take the function which is relu minus x plus x, okay, which is, by the way, just a relu function, write down what it means, and you take the derivative at 0 of this function, it tells you it's 1. Does it make sense? Yeah. The slope on the right part is 1. So why not? The issue now is that, so this is still a convex function. If you take now the difference between this function and the only one, okay? So Euler, the function is 0. And you ask him what is the derivative of the function identically equal to 0 at 0, it tells you that it is 1. Does it make sense? No. Okay, so it does not make sense. And still, when you do backpropagation of any networks which have the volume inside, I mean, there is absolutely no issue with this kind of property. So how can we somehow fix the math and not try to fix the algorithm here? But I don't want to say I want to change the algorithm such that the math makes sense. The algorithm works. Okay, there is no issue. The backpropagation with JAX is doing its stuff. So what kind of math we can do such that these things make sense? So this is a bit, let's say, not that hard, but we need some definition here. So if you take just the classical convex subgradients, you will have the issue that we are playing with functions which are not convex. Okay. So we need to do something a bit more smart. When you are trying to do non-smooth analysis with non-convex function, you have an object which is a Clark differential, which could make sense, but it is not compatible with the chain rule. What is automatic differentiation? Automatic differentiation is just applying the chain rule iteratively. Okay, this is absolutely wrong in practice, but from a theoretical aspect, automatic differentiation is applying the chain rule. How we can design a function, a subdifferential such that it is compatible with the chain rule. So the answer is that if you look at this question as the operator theory question, the answer is it's not possible. You cannot have the the same chain rule on the whole space is too much. But what you can do is to ask the chain rule to be true along any Lipschitz curve. So we are telling you, yeah, that's the same thing. Exactly. That's the same thing in the sense that in practice it will change absolutely nothing asking to be true on any Lipschitz curve. But in terms of math, you fix everything by asking it to be true only on this curve. So when you have a function that satisfies such equation, okay, this quantity, so V here, this operator, you will call it a conservative gradient. The nice thing is that if you are familiar with Clark's differential, you can prove that it is always contained inside any conservative gradient. When your function, so not when, sorry, since we are playing with functions which are Lipschitz, what you can see is that almost everywhere you will get back the good notion of derivative. So it means that here you will get a singleton which is 1, and here you will get 0. And the important fact is that if you do the sum or the composition of two functions which are path differentiable, you still have a function which is path differentiable. So this is yet another way to define subgradients for a non-convex function, but which has a good property to be compatible with the chain rule, aka the automatic differentiation. Question?
So if you use this definition and run the example of the previous slides, we get 1. We can get no function here. Now in the ReLU example, in the JAX example of the previous slides,
you get -1, you get 0, 1. And that's a good answer because you cannot give it another 1. So what I mean is that here, JAX is telling you that it is 1. Okay, but if I reverse the role, I can get also 0, and I can also play with some parameter. It can give you one half. Okay, so the answer here, the conservative gradient associated with it, you can show that it is 0, 1.
0, 1?
Yeah.
So like
the segment.
Yeah, okay.
And it coincides with the classical subgradient. But in a way where you can show that it was with the chain rule.
So, so is it obvious like every function is path differentiable or
No.
no? Okay.
No. You can construct arbitrarily weird stuff, but
Okay.
what we can discuss a bit later is the fact that absolutely every function in machine learning, but really this time every function in machine learning is path differentiable.
Okay.
And also, does that mean that is that a lot of impact on the differentiation algorithm?
An impact on the algorithm?
Yes.
None. Okay. So the impact is just, as I said, is to fix the math and not fix the algorithm. Is to give you, so this conservative gradient stuff give you a way to say that everything that happens when you play with something like I will come back in a moment. You will see that. Okay. Everything that you do when you use a true automatic differentiation framework is valid in this setting and is not in a classical Clark differential one.
So yeah, basically you're changing your class of functions to be slightly more restrictive.
Yeah.
But it's so yeah, it's a bit more general than functions that are differentiable almost everywhere.
Yeah.
It's in between.
No, it's slightly smaller because you are asking them at least to be locally Lipschitz. So you know that it is differentiable almost everywhere.
Okay.
And in addition, you don't want weird things which are too weird with respect to the chain rule.
Okay.
I still didn't understand what happened in the previous example. You said, because the last function is 0, right?
Yeah.
And you said the answer will still be either 0 or 1.
Yeah. So here it's because the Jacobian that you compose here, this function, so this is the difference between function and program. Here you are considering this program as somehow the sum of this program and this program. And the conservative gradient associated to this program is 0, 1. Obviously not to the function 0, but somehow you never, that's why I wrote it like that. I never rewrite it as 0. I'm just saying that this is the sum of two functions, but augmented, so let's say two programs. But yeah, thanks for the question, because it does not fit the fact that if you reduce everything, you have 0 on one side and 0, 1 on the other. Just fix to say, okay, Jax told me that. Jax is right. You see that this is really, so here I'm not trying to fix Jax. This is the answer of Jax. I just want a framework to explain what happens for it. Yeah.
There is something very weird because
Yeah.
usually when you define a function, you just define its value pointwise. But here you are actually, you need to take into account how this value is computed. You need the computational graph of the,
Yeah, true.
which is not in the definition here.
Which is not in the definition in the sense that, okay, then let's discuss after about it. I try to keep the thing. This thing is not that too technical, but yeah, there is the question of reduction, which is not all right.
Okay.
Okay, so I gave you a definition here about a non-smooth iterative program, okay, a way to differentiate through it. But I just want to point out something. So I'm going back to this example that I just highlighted, which is the minimization of smooth function. So let's start with the smooth, non-smooth. What I will look at in the first instance is a function which is C1 with a Lipschitz gradient. So you know that almost all the theory of gradient descent is linked to functions which are C11. Okay. On the other side, we will discuss what happens when the function is C2. So maybe you could apply Newton, but you will not apply Newton. You still keep first order algorithm. So the funny thing is that the minimization of this problem, the minimization of this function is a non-smooth algorithm. And the minimization of this problem is a smooth algorithm. What does it mean? It just means that here you have enough regularity to say, okay, I have a gradient. Oh, sorry, here, the gradient is C1. So, okay, I have a smooth function here, f. The function is smooth, is C1. But if you are in the natural setting here, C11, so absolutely every theory are based in this case, the algorithm itself with respect to f and theta is not smooth. It's clear enough. But I'm saying that minimizing smooth function, if you look at the algorithm, if you have enough regularity, which is not a typical assumption, it's a smooth problem, and you can apply Gilbert algorithm, Gilbert theorem to say that everything is nice. But this is not the case for the classical C11 setting. Yeah.
So it's so you mean smooth here means differentiability of f, not continuous f.
Yeah.
Because the left was
So here,
differentiability.
here you are not typically differentiable because you have lost one derivative. So this thing is merely continuous. Okay.
Can you remind me what C11 means?
So
exactly?
sorry, C11, that's C11 is C1 with Lipschitz gradient. And C2, okay, is just to have your derivative, which are all the second derivative exist and are continuous. Yeah. Okay. So the fun fact is that when you wrote down the definition that I gave just a bit earlier, everything is simple. So if you admit the existence of this subgradient, of this conservative gradient, what you can do is at this time, instead of doing the propagation of the gradient of the derivative, you have set valued mapping, okay, which is a conservative gradient, and you just do exactly the same recursion. So what I mean here is that, so this definition looks complicated, but if now you pick an example, what I'm telling you is that you take one example here of the previous iterate derivative. You take one example here, okay, because potentially you have multiple of them, and this linear recurrence gives you the next Jacobian, the next iterate Jacobian. Okay, and if you want the whole set from a theoretical perspective, it's just to say that this is all linear affine combination when AB travel inside this together. Okay, so you are doing exactly the same thing. This is in some sense you fix what Jack's doing. Jack is doing that. He should at each step one derivative, okay, and he do it like it was differentiable. And so what we are going to see is that when you do that, things works out. Okay. So here I told you that we can define somehow the non-smooth cumulative differentiation. Accelerating just a bit, what happens, I won't enter all the details, but if you have a similar assumption, so you bound the same spectral quantity, okay, what you can show is that in some sense, you have the convergence of your Jacobian, okay, of the iterate, towards the Jacobian of the limit, and it exists. We can discuss the math really inside it later if some of you are interested. But just to tell you that everything is played well in this non-smooth world when you use this subgradient. Okay, so we have defined this object, which is a priori not really obvious to understand, okay, but it exists, okay, and you can say that this is the limit of the Jacobian and the diagram commute. Okay, but it looks complicated. Yeah, right.
The brackets don't go into the end of the parenthesis. I'm wondering which quantity you're.
This is the whole. So this is a fixed point as state valued mapping, and I will clarify just in a sec. So the important part is that for almost all theta, you are playing with Lipschitz function, and it do exactly what you want. Okay, it tells you that even if it's not smooth, almost everywhere it's not an issue. You recover the same Jacobian as before. Okay, so the summary is that I introduced you an object which somehow fixes the math behind analyzing what happens when you do automatic differentiation of something which is non-smooth. And the sum up is that, okay, but it gives you what exactly you expect, almost for all theta. Okay, and so this is the same diagram, but this time we cover some not nasty object, but just almost everywhere. Another thing, so to answer your question, is that if in addition you ask a bit more about the function f, okay, so somehow the fact that the function is semi-algebraic, then you recover also the fact that the convergence is linear, okay, of the derivative. And I want it this way, just nothing else, just to tell that our proof is suboptimal, because here in the smooth world, we will get rho over t, and here we get rho in terms of, this is due to the proof, we only have t over 2 as a but this is still a linear rate. Okay, I will, yeah.
So that means on the sides, that means that if the function was a net repeats the gradient selection, then okay, the limit goes to infinity, but it's like a uniform comparison. So I think that at infinity is equal to 0, but before we cannot.
It's uniform.
It's uniform, okay. So I think that it's continually going to 0,
Yeah.
you just don't know the rate.
Exactly. Okay, and so just to finish, we say that many people are doing implicit differentiation in practice. So surely you can do something similar, right, in the non-smooth form. So the answer is yes. Using the same notion of conservative Jacobian, okay, you can show that this guy, so simply instead of being just a one element, it's some set, okay, this guy is a conservative Jacobian for the limit. So these two guys are the same, right? Right. No. So the point is that in the non-smooth world, this is something that you cannot fix. When you are doing implicit differentiation, you recover strictly less information than doing automatic differentiation. Again, in practice, almost everywhere, everything will play nice. So it will not change your machine learning algorithm. But from a theoretical aspect, this is a way to say that this thing is strictly less powerful in terms of expressiveness than doing the automatic differentiation. Okay. Not saying that there is a strong practical implication of that, just as a theoretical object, one is strictly more powerful than those. Okay, yeah.
You say powerful, you just mean larger in the sense.
Yeah, but I mean, since you don't know a priori where are the good information, yeah, right. It's one is strictly larger than the other one, but you may have one derivative going at this point, and you cannot express that with implicit differentiation in this sense.
Yeah, but in practice, it means that your algorithm will pick, you don't know which direction your algorithm will pick in the set of ways.
Yeah. Yeah.
So just as an example, for instance, imagine this, say on the regular example, maybe with implicit differentiation at 0, we might get like 0.1, 0.9 instead of 0.1.
For instance,
That's
yeah.
an application.
Yeah, exactly.
So at the point where the function is not smooth, we might not get the full range
Exactly.
of the subderivative. Meanwhile, the autodiff does.
Give you, yeah. You can also, I can give some example at the end of some a concrete example where it actually happens, but still general. Okay, and just to go back to the fact that no one's are computing full Jacobian in practice, so you are doing either forward mode, backward, or reverse mode of automatic differentiation. Everything that I say is still true when you are doing propagation forward, the forward mode or the backward, the reverse mode of automatic differentiation. Okay, this is something that you can observe in practice on non-smooth problems. So for instance, if you are doing fluid regression, the lasso, sparse industrial covariance matrix, or trend filtering, if you just run them in JAX like that, you will get this linear convergence rate after the manifold identification, whatever. But you can observe this linear rate also in the non-smooth. Okay, and yeah, sorry, just one last comment, which is I think a fun one. So let's say now that you are doing something a bit more involved than the gradient descent, okay? And you want to use, for instance, the heavy ball. So a momentum method, not an adaptative one like Adam, but just a simple regular heavy ball method. What you can show is that if your function that you try to minimize is C2, okay, then the Jacobian of the iterates of this algorithm converge. Okay, so everything is nice. The fun fact is that if you are doing it for C11, even for function in one dimension, you can show that the derivative does not converge necessarily. So this is a case where smooth stuff is working well. Okay, so automatic translation of smooth algorithm is working, but not for non-smooth ones. Okay, and just to tell you here, the function behind it is just a piecewise quadratic function, something really simple, and you can observe it numerically what happens. Okay, so I think I will conclude here. just to say that one thing that I didn't tell you about the optimal transport case is that, so the issue was that the spectral content, this larger singular value is strictly equal to 1. And we would like to have, so since this is the major issue, because if it's strictly bigger than 1, you cannot do anything, okay, everything will diverge. We want to have something which can be applied to this, let's say, a frontier case. Also to understand what happens when you have acceleration. And we recently have a result on what happened in the stochastic work. So obviously we are not doing typically gradient descent, but stochastic gradient descent. And it's works somehow in the same way that's what I presented today. And there is also this paper, which is linked, if you know, about Jacobian free backpropagation. But we studied a bit what happened when you do, let's say, when you try to modify a bit the backpropagation to go a bit faster. Okay, thank you.
Yeah, thank you. So we have plenty of time for questions.
So we just want for heavy ball, what you're saying is like the fixed point operator is not C2.
So here, the function, so if I take f theta to be C11, the function that I minimize,
Okay, F theta, okay.
the big F is merely continuous. So it's not non-smooth in the sense that you have a break, but it's just continuous, you cannot differentiate. Okay.
Yeah, so the iterates are still converging, right? The heavy ball.
So yeah, sorry, I didn't mention it, but the iterates converge, but not the derivative. When the iterates does not converge,
Yeah,
I mean,
So if we were to 1, we would be good.
no, but if you are C2, you are okay.
Sorry, yeah.
So there is not really something really very interesting between C11 and C2.
So how does it? How does it doesn't contradict the previous results? But like the theorem we had was that like for non-smooth it was working, no?
So okay, now but here it was okay. Just to be sure, when you say contradicts here, so you will have the good let's say this guy will be still what you sorry. Why does it not contradict?
But because maybe it's not that differentiable or something.
No, it's not differentiable, but the point is that here what happens is that it contradicts the operator big F here as a singular value which is strictly bigger than 1.
Okay.
Sorry. So let me just so you here. Yes. So what you have is that you have this AN value in this case, which is strictly bigger than 1, and everything collapses.
So it's if you choose a good beta, you should be safe. Beta is close to 0, no?
Yeah, you can fix it. This is for a set of parameters for the heavy ball. It's not uniformly for all parameters of the heavy ball.
If you use the heavy ball parameter advocated by Polyak,
Yeah.
you get
Yeah, you're right. But I think if I use the Polyak parameter, I think I can.
I mean, it will not converge because it conversion for quadratics. So yeah, if you use the one from Polyak, there is actually an example that shows that Polyak's actually
Yeah. Thank you.
So yeah, of course. But so your counter example is for a specific parameter.
Yeah, it's not uniform the parameter. No. No, I mean it's a bit degenerative.
Yeah.
We need for one very specific
break,
yeah.
But also that means that if we are using like accelerated methods for finding for the diff, it might actually not working because usually accelerated method have a bigger similar value compared to
So we worked a bit. We have a note on for Nestor case, but it's essentially tell you that you can find stuff where everything breaks in this similar fashion. But we think that maybe we can fit and give this time a range of parameters where stuff goes up, but it's not finished. And the students starting on that manner on this topic.
But might it happen that actually the range of parameters where we can use autodiff might be through an algorithm which is like as fast as version descent?
Possibly.
Okay.
I don't have an answer on that, right? But it's possible.
Related questions. So in the C2 case, you don't have this eigenvalue problem?
No.
So it's because it's C11 that you can construct eigenvalues.
Exactly. This is really the break that allow you this choice of 2 and 8 is clearly linked to this quantity. If I don't remember, I have the computation, but if you change slightly this quantity, you will find something different.
I see.
But what is funny, like, okay, this is pathological, but somehow you can imagine stuff where you define things in a piecewise manner and things like that happens. It's not it's not a very nasty function.
Mm. You could imagine that a lot of non-linearities could have, non-smoothness could have
Similar stuff, and you are doing
I think neural networks satisfies that case actually.
Yeah.
Also that.
But again, that's the point that this is for a specific set of parameters. When you are training neural network, you have more difficult questions like understanding 3D as a derivative, if you are when trying or not. But it's more to study what happens on the scale of one layer, which is well defined, where you can control everything. And if you have issue to proving the convergence of the iterates, why care about the derivative itself?
The fact is that even if you can find a very specific set of parameters of equal and very specific function where everything fails, I think in practice we won't encounter such cases.
Yeah.
But that could also mean that it might happen that we are in some cases where it convergent infinity, but it may take forever for convergence.
And one fun thing here that I didn't cover is that in the stochastic case, so you know that here in the stochastic case, so you have either you converge when you are with, for instance, a fixed step size, you converge to a noise ball. The other thing is that the iterates will also converge towards a noise ball, slightly bigger. We have also results of what happens when you have decreasing step size in a similar fashion. And the first thing is that in the interpolation regime, so you know that SGB sometimes converge linearly. And we have identified two regimes where either you have linear convergence of the iterates, but convergence to a noise ball of the derivative, or double interpolation regime. So it's fun. I think that was not really explored what happens on this level. So there is a double interpolation where it's kind of illustrated.
Other questions? Yeah, one last maybe. Just trying to wrap up the thing. So automatic differentiation is a convergent process, even in the non-smooth case.
Yeah.
Under strong assumptions.
And they're very strong.
So like, is it stronger in the non-smooth case than in the smooth case?
Not really.
It's always Jacobian eigenvalue smaller than 1. And
no, it's not. So if you read between the line as an optimizer, what we are saying is that everything is playing nice in the strongly convex case, locally strongly convex case, and we cannot say way more about that. But it's normal because when we are analyzing optimization algorithm as a fixed point method. Fixed point method means somehow strong convexity. It's really there is a small gap between the two notions, but at the end we are using stuff which makes sense in the strongly convex case. So this is absolutely not true for let's say what happens if you want to differentiate through a parameter of neural networks training like that. Very limited scope. Strong convexity is an interesting case to write that.